In 2023, physicists at University College London ran an experiment designed to answer one of the most unsettling questions in modern science. The result did not simply challenge our understanding of quantum gravity. It quietly reopened a question that most scientists are reluctant to ask out loud, whether the universe we inhabit was built rather than born. I want to be precise about how I frame what follows, because there are two versions of this conversation. One sounds like philosophy. The other is pure physics. I am only interested in the second one. What the UCL team found, and what several independent research groups have been circling for the better part of a decade, is that gravity refuses to behave the way every other fundamental force in the universe behaves. And that single stubborn refusal may be the most important clue we currently possess about the nature of reality itself, not metaphorically, mathematically. Every force we know of electromagnetism, the strong nuclear force, the weak nuclear force, has been successfully described using quantum mechanics. We can write equations treating those forces as quantum fields, as things that exist in superposition, as things that are fundamentally probabilistic at small scales. Those equations work with a precision that is genuinely difficult to overstate. Quantum electrodynamics makes predictions accurate to 1 part in a trillion. That is not an approximation still being refined. That is a description of nature, so exact it should stop you in your tracks. And then there is gravity. Gravity governs every planet, every star, every galaxy, every large-scale structure in the observable universe. Einstein described it in 1915 with general relativity, a framework that is spectacularly accurate at the scales it was built for. Gravity works beautifully, right up until you attempt what was done successfully with every other force. When physicists try to quantize gravity to write a quantum description of it the same way we have for everything else, the mathematics does not merely struggle, it collapses catastrophically. The equations produce infinities, not large numbers, infinities. Values that are not just incorrect but entirely meaningless. This has been true for nearly a century. The most capable minds in theoretical physics have been attacking this problem since the 1930s. String theory is largely an attempt to solve it. Loop quantum gravity is another. Neither has produced a single confirmed experimental prediction. Not one. I want to be honest about what that means because popular science tends to either catastrophize it or dismiss it entirely. I have spent a significant portion of my own career working in theoretical frameworks involving extra dimensions. The Randall-Sundrum model, which I developed with Raymond Sundrum in 1999, was itself an attempt to understand why gravity is so much weaker than the other forces, why it appears to occupy a different geometric space than the particles it acts upon. And what I can tell you from inside that work is this. Gravity's resistance to quantization is not a technical inconvenience we simply haven't resolved yet. It may be communicating something fundamental, something whose full implications we are only beginning to grasp. The UCL experiment, led by Sugato Bose and a team that included Anupam Mazumdar, was designed to test whether gravity can generate quantum entanglement between two masses. This is called the BMV Experiment, named for Bose, Marletto, and Vedral, who proposed it independently in 2017. The logic is elegant. If gravity is quantum in nature, if it is mediated by a particle called the graviton, the way electromagnetism is mediated by the photon, then it should be capable of doing what quantum fields do. It should be able to create entanglement. Two masses interacting exclusively through gravity should become entangled if and only if gravity operates at the quantum level. That is the prediction. That is the test. And the answer, whichever way it falls, is going to force a reckoning with questions physics has been avoiding for 100 years. The BMV experiment has not yet been executed at the scale required to produce a definitive result. That precision matters, so let me be clear about it. We are still building toward the conclusive version of this test. The technical demands are severe. You need to isolate two small masses from every other interaction in the universe, maintain them in quantum superposition long enough for gravitational interaction to occur between them, and then measure whether entanglement has formed. The noise floor required is beyond what most laboratories in the world can currently achieve. But the fact that this experiment is now being funded, designed, and partially executed by some of the most rigorous experimentalists in quantum physics tells you something important about where the field stands. We are no longer purely theorizing about whether gravity is quantum. We are constructing machines to find out. Here is where the story takes a genuinely strange turn, and I need you to stay with me, because what follows is not speculation. It is a direct logical consequence of the physics, and it is one of the most underreported ideas in contemporary theoretical science. If the BMV experiment runs and the two masses do not entangle, that result would be extraordinary. It would mean gravity is not quantum. In a universe where every other force is quantum, gravity would be something categorically different. That would be a result without precedent in the entire history of physics. And it would make a specific set of ideas about the nature of reality suddenly far more plausible than they are currently treated as being. One of those ideas comes from the work of Roger Penrose and Lajos Diósi, who independently proposed in the late 1980s and early 1990s that quantum superpositions collapse, that wave functions resolve from multiple possibilities into single definite outcomes precisely because gravity is not quantum. Their model, known as the Penrose-Diósi model or objective collapse theory, suggests that quantum states are fundamentally unstable in the presence of spacetime curvature. That gravity, in other words, is the mechanism that compresses quantum possibilities into classical facts. That the universe becomes physically real in the sense of collapsing into definite states through gravitational interaction. If that is correct, gravity is not simply a force, it is the enforcement mechanism of classical reality. It is the process by which the quantum world, probabilistic, superposed, genuinely plural, gets compressed into the single definite world we actually experience. The reason physicists cannot quantize it is not that their mathematics is insufficient. It is that gravity does not operate within the quantum layer. It operates at the level of reality selection. It is the interface between the possible and the actual. That deserves a moment of genuine attention, because it tends to get glossed over too quickly. We are accustomed to thinking of physics as a hierarchy of scales. Small scales are quantum, large scales are classical, gravity governs large scales, and quantum gravity is presumably the small-scale version we haven't worked out yet. That is the standard assumption. But Penrose and Diósi are proposing something structurally different. They are suggesting the relationship runs in the opposite direction. The classical world does not emerge from quantum mechanics in spite of gravity. It emerges because of gravity. Gravity is the reason a classical world exists at all. Now let me bring in simulation theory, not the popular philosophical version, not the probability argument about the ratio of simulated realities to base realities, which is a genuinely interesting argument but is not what I am focused on here. I am focused on a specific, testable, physics-based version of the question. If you were designing a computational system, a universe running on some kind of underlying information processing substrate, what would be the most expensive thing to simulate? The answer, from a computational physics standpoint, is quantum superposition. The resources required to track every particle in every possible state simultaneously scale exponentially with particle count. A universe of truly quantum everything, simulated in real time, would require resources that are, under any realistic assumption, larger than the universe itself. This is not a new observation. It is part of what motivated Richard Feynman to propose quantum computers in the first place. He demonstrated that the only system capable of efficiently simulating a quantum system is another quantum system. Classical computers cannot do it. The mathematical space involved is simply too large. So here is the question that follows directly from that, and every step of this logic is grounded in established physics. If the universe is a computational system of some kind, the most efficient version of that system would not render full quantum superposition for every particle at every moment. It would maintain quantum behavior only where it produces observable effects, only where measurement occurs, and everywhere else it would default to a less resource-intensive representation, a classical one. Now consider what quantum mechanics actually does. The wave function, the complete quantum description of a particle's state, exists in superposition until the moment of measurement. At that moment, it collapses. The multiple possible states resolve into one definite outcome. This is wave function collapse, and it is one of the most debated features in the entire history of quantum theory, because no one fully agrees on what causes it or what it means at the deepest level. The Copenhagen interpretation says collapse happens through measurement without specifying what measurement fundamentally is. The many worlds interpretation says collapse never happens, the universe simply branches. Objective collapse theories like Penrose-Diósi say gravity causes it. Decoherence theory says the quantum state becomes entangled with its environment and appears classical from any local perspective without ever truly collapsing. What I find genuinely striking, and this is not a mainstream position, this is me following the logical thread of the available evidence, is that the computational simulation framework and the Penrose-Diósi gravitational collapse framework make nearly identical predictions about when and where quantum behavior should transition to classical behavior. Both say quantum behavior persists until the system becomes large enough or massive enough for gravity to matter. Both say the transition from quantum to classical occurs at the gravitational scale. Both say the classical world is not the universe's default state, it is something that must be produced, something that must be enforced, and gravity is what enforces it. That convergence is either a coincidence or a clue. I cannot tell you which one yet. Nobody can. But the physicists most seriously engaged with the BMV experiment are also the physicists most seriously engaged with what the quantum measurement problem actually implies about the structure of reality. These are not separate conversations running in parallel. They are the same conversation viewed from different angles. One more piece of evidence deserves attention here, because it meaningfully shifts the texture of the entire question. In 2023, a paper published in Physical Review Letters by Jonathan Oppenheim at University College London proposed what he called a post-quantum theory of classical gravity. The core claim is this: gravity and quantum mechanics can coexist without gravity being quantum, provided that gravity introduces a fundamental, irreducible randomness into the fabric of spacetime itself. Spacetime is not smooth and classical in the way Einstein described it. It fluctuates, it jitters, but those fluctuations are not governed by the Schrödinger equation. They represent a different category of randomness, a classical randomness embedded in the metric of reality at its deepest level. What Oppenheim's model predicts is that gravitational measurements made at sufficiently small scales will reveal noise, not the quantum noise of Heisenberg uncertainty, which we already account for, but a structurally different kind of noise with no quantum origin whatsoever. Noise that comes from spacetime itself being fundamentally, irreducibly imprecise. He calls this a decoherence diffusion trade-off, and he has proposed specific experimental tests capable of distinguishing his model from standard quantum gravity approaches. I want to be honest about how this work was received, because the context matters. When the paper appeared, it was not universally embraced. Several prominent quantum gravity researchers found the mathematical framework underdeveloped. Others considered the proposed experimental tests too technically demanding to be actionable in the near term. These are legitimate criticisms, and the scientific community is still working through them. This is what science looks like from the inside, not a clean arc of discovery and confirmation, but a contested, complex argument about what the evidence is actually saying. But here is what I find genuinely significant about Oppenheim's result, regardless of whether his specific model ultimately proves correct. The fact that it is possible to write down a mathematically consistent theory in which gravity is not quantum, in which gravity and quantum mechanics coexist without gravity requiring quantization, means that the assumption gravity must be quantum is not a theorem. It is a preference, an aesthetic choice, a scientific bet, and the experimental evidence accumulated so far does not definitively rule out the non-quantum option. We are currently in a period of genuine openness on this question, and only experiment can resolve it. This brings me back to the simulation question, and I want to make the connection explicit rather than merely suggestive. A computational universe would need a mechanism to manage the transition between quantum and classical regimes. It would need behavior that appears quantum at small scales probabilistic, superposed, producing interference, and behavior that appears classical at large scales definite, local, causal. It would need that transition to be sharp enough to prevent quantum effects from propagating visibly into the macroscopic world, which is, to a remarkable degree of precision, exactly what we observe. Quantum behavior dominates at subatomic scales. Classical behavior dominates at human scales. The transition happens somewhere in between, and the exact mechanism remains the most actively contested foundational question in quantum mechanics after a full century of debate. What gravity does in the Penrose Diósi model is serve as the natural cutoff, the natural rendering limit, to borrow the language of computational systems for a moment. A particle in superposition remains in superposition until its gravitational self-energy, the energy associated with the spacetime curvature produced by its own mass, becomes large enough to destabilize that superposition. At that point, the wave function collapses, the particle becomes classical, the world becomes definite. And the scale at which this happens, called the Diósi-Penrose length, or the gravitational decoherence scale, corresponds roughly to objects sitting at the boundary between quantum and classical behavior in our actual lived experience of the world. A universe designed to appear quantum at small scales and classical at large ones, with gravity as the mechanism of transition, would look exactly like a universe in which gravity is the last force to be quantized and in which that quantization never fully works, because gravity is not a force operating within the quantum layer. It is the boundary condition of the quantum layer. It is the edge of what gets rendered. It is the horizon of the simulation, if the universe is a simulation. I want to be precise about what I am claiming and what I am not. I am not asserting the universe is a simulation. I am not presenting that as a conclusion. What I am saying is that the specific pattern of physics we observe, quantum behavior below the gravitational scale, classical behavior above it, an inexplicable failure to quantize gravity, a measurement problem that has resisted resolution for a century, is precisely the pattern you would expect to find if reality had a computational structure with a gravitational rendering limit. That prediction is falsifiable. If the BMV experiment succeeds and gravity generates entanglement, it would provide strong evidence that gravity is quantum, removing one of the key pillars of this pattern. If the experiment fails, if gravity proves stubbornly classical even at quantum scales, the pattern becomes significantly harder to explain without invoking something genuinely unusual about the nature of spacetime itself. The physics I find most worth pursuing has always lived at the boundary of what we can currently explain. And the boundary that has occupied most of my attention in recent years, not just in public discussions, but in technical conversations with colleagues at Harvard, at conferences, in the margins of papers read late at night, is the boundary between quantum and classical reality. Between the world described by the Schrödinger equation and the world we actually inhabit. Between the possible and the actual. That boundary has a name in the foundational literature. It is called the Heisenberg cut, and nobody knows precisely where it falls, why it falls there, or what enforces it. But every candidate mechanism we have, decoherence, objective collapse, many worlds branching, consistent histories, shares one essential feature. They all require something at the boundary, something that performs the work of making the quantum world classical, something that selects, something that renders. Gravity is the only candidate that connects directly to both the foundations of quantum mechanics and the large-scale structure of space-time simultaneously. It is the only force that touches both layers. It is the only force that is simultaneously too weak to quantize easily and too fundamental to set aside. And it is the only force that, if Penrose and Diósi are correct, actively produces classical reality rather than merely participating in it. There is a version of this conversation that ends here with a dramatic pronouncement about what all of this means. I am going to resist that, because the honest answer is that we do not know yet. The BMV experiment will run. Oppenheim's model will be tested. Penrose's objective collapse predictions can in principle be verified or falsified. These are no longer philosophical questions, they are experimental questions. And experimental questions, unlike philosophical ones, have answers. The universe is going to tell us something. The task is to build instruments precise enough to hear it. Now let me go one level deeper, because there is a piece of this story that almost never appears in popular discussions, and it changes the weight of everything described so far. When we talk about the failure to quantize gravity, the tendency is to frame it as a technical obstacle, a mathematical problem that will eventually yield to sufficiently sophisticated formalism. But there is a minority position in theoretical physics, held by serious researchers and published in serious journals, that the failure is not technical at all, that it is ontological. That gravity resists quantization not because we lack the right mathematical language, but because gravity is not, at its deepest level, the same kind of thing as the other forces. That it belongs to a different category of physical reality entirely. The clearest expression of this view comes from work on emergent gravity. The idea, developed most rigorously by Erik Verlinde at the University of Amsterdam, is that gravity is not a fundamental force. It is a thermodynamic consequence, an emergent property arising from the statistical behavior of information at the boundary of space-time. Verlinde published a paper in 2011 Inches, the Journal of High Energy Physics, arguing that gravity arises from entropic forces, from the tendency of systems to move toward configurations of higher entropy in the same way, that pressure and temperature emerge from the collective behavior of molecules. No individual molecule has a temperature. Heat appears only at a higher level of description. Verlinde's proposal is that gravity works the same way. It does not exist at the fundamental level. It appears when you zoom out far enough. If Verlinde is correct, and I want to be careful here, because this remains a contested and actively developing research program, not a settled conclusion, then asking why gravity cannot be quantized is like asking why temperature cannot be quantized. Temperature is not a fundamental quantity. It has no quantum version because it does not exist at the quantum level. It exists only as a statistical description of many quantum interactions occurring simultaneously. Attempting to write a quantum field theory of temperature would be a category error. Verlinde's argument is that writing a quantum field theory of gravity is the same kind of mistake. We are trying to quantize something that only exists because we have already averaged over the quantum level. This is a radical claim. I am presenting it not as established physics, but as a logically coherent possibility that has been taken seriously by a substantial number of physicists, and that connects meaningfully to other well-established results, particularly the Bekenstein-Hawking entropy of black holes, which demonstrated in the 1970s that thermodynamic quantities like entropy and temperature are not merely analogies for black holes, but actual physical properties. The connection between gravity and thermodynamics is not new. Verlinde's contribution is to reverse the direction of the arrow. Instead of gravity producing thermodynamic effects, thermodynamics produces gravity. Connect this now to the simulation framework, because the connection is direct and it is not something I invented. If gravity is an emergent thermodynamic property of information processing at the boundary of spacetime, then the most natural substrate for a universe containing gravity is not a physical one. It is an informational one, a computational one. A universe in which the fundamental currency is not matter or energy but bits information, and in which gravity emerges from the way that information is stored, processed, and distributed across the boundary of the system. This is not a metaphor. This is the literal implication of combining Verlinde's emergent gravity with the holographic principle, the well-supported idea, arising from black hole thermodynamics and string theory, that the information content of any region of space is encoded on its boundary rather than its volume. A three-dimensional universe whose physics is encoded on a two-dimensional surface is not a physical system in the conventional sense. It is a system in which what appears to be three-dimensional physical reality is a projection, a rendering of information organized on a lower-dimensional substrate. The holographic principle is not fringe science. It is taken seriously by a significant fraction of the theoretical physics community. The ADS CFT correspondence, developed by Juan Maldacena in 1997, is a concrete mathematical realization of holography in certain spacetime geometries, and it has generated thousands of papers and produced genuinely useful results in both string theory and condensed matter physics. I am not citing it as proof of simulation theory. I am citing it because it demonstrates that the idea of physical reality being a projection of information on a boundary is mathematically rigorous and scientifically productive. It is not a loose analogy. It is a framework with technical content. What emerges from putting these pieces together, emergent gravity, the holographic principle, objective collapse theory, the persistent failure of quantization, the measurement problem is not a proof of anything. But it is a coherent picture, a universe in which reality is informational at its foundation, in which quantum behavior is the native language of the underlying system, in which classical reality is produced by a gravitational rendering mechanism operating at the boundary between quantum and classical scales, and in which gravity resists quantization because it is not a feature of the quantum layer, but a property of the system's informational architecture. That picture is consistent with everything we currently observe, and it makes predictions that experiments now being designed can test.